All right, let's do one more disk method with a vertical axis of rotation. Now in this case, we're just going to be asked to set up the integral rather than actually evaluate it, because honestly, that's usually the more difficult part of problems like this. Is just kind of visualizing and understanding the geometry involved to get it set up. So in this case, we're going to consider the region bound by x equals 2y squared. So now we know this is a tipped over parabola like before, and the line x equals 4. And we're going to set up the integral used to find the volume if we revolve it around the line x equals 4. So let's get a little bit of a sketch going on over here. So if we've got, here is our y-axis, and our x-axis is this curve is a function of y. So again, we've got ourselves this little tipped parabola, and this is x equals 2y squared, and then we are asked to bound this at the point x equals 4. So if we go out to x equals 4 and bound that, the region we are considering now is this one right here. So a very similar setup, but the actual region that results is a little bit different than before. So sorry, let me finish shading this in. All right, so this is our region, and now what we need to do is we need to consider if we are going to rotate this about the line x equals 4. How would we calculate that volume? All right, well, we've got a sketch already, and then don't forget our cross section. This is going to be particularly helpful here. So remember, our cross section is going to start on our axis of rotation, and it's going to go out to our boundary curve. So we're going to start here on our axis of rotation. I'm just going to pick a spot right there, and we're going to go out to our boundary curve. So here's one of the cross sections of area that will be rotated around to generate a disk. And again, we know it's going to be a disk because it's right against the axis. It's going to be a solid circular disk. So bounds would be the next thing we need to consider. Now in this case, we weren't explicitly given our bounds, but we do know that they're going to be y equals something. And we're going to do this similar in fashion to the way we did that second problem we did. Is we're going to take our two curves, 2y squared and x equals 4, set them equal to each other, and solve. And if we divide and then solve, we're going to get y is equal to plus or minus the square root of 2. So the bounds that we're going to consider are going to be from y equals the negative square root of 2 to y equals the positive square root of 2. All right, so we got that taken care of, and now this is one of the trickier ones that you'll come across, is to find the radius here. Now remember, the radius is generalized as the distance from the axis of rotation here to our boundary curve here. So how do we generalize this distance? So this is our radius. R is a function of y. Now in this case, this line will always be, let's see, so get another color to contrast it. So since we know that this distance right here will always be 4, and we know that this distance right here will always be 2y squared, we would need to subtract those two differences, those two distances, to get what's left over. So what we see that happens here is that this outer radius is going to be that full distance 4, and from it we subtract that 2y squared. And that gives us our radius as a function of y. So we can go ahead and we can define that now. So our radius, r of y, is going to be equal to 4 minus 2y squared. And now we can go ahead and we can just set up that volume integral. So volume is going to be equal to the integral from negative square root of 2 to positive square root of 2 times pi times our radius squared integrated with respect to y. And if you all noticed while I was working through this that it would be easier for us, since it's symmetric again, to just say that it's twice the integral from 0 to the square root of 2 times pi times 4 minus 2y squared dy, then that would have been a great observation, and that would be true. In this case, we were only asked to set it up, so we don't need to carry it out any further. But if we did need to integrate, we would FOIL out the 4 minus 2y squared, and then evaluate. But this seems like a pretty good place to stop for this one. Okay, so we've gone over 4 different examples using the disk method. Horizontal and vertical axes, and then each case an axis, either the x or y, or some other line that we had to rotate about. So hopefully those will be enough to kind of get you started with the examples in the homework. Because the next thing we're going to do is we're going to consider another method alternative to the disk method called the washer method.